Okay. Good morning, participants. Once again, we welcome you all to the 5 days Atal-sponsored FDP on the role of additive manufacturing in the era of Industry 4.0. So today we are at the last day at the second session. This session is going to be handled by Dr. Indrani, professor from IIT Kharagpur. It is our great pleasure to welcome Indrani madam to this wonderful FDP. Welcome you, madam. Dear participant, it is my pleasure to introduce Dr. Indrani madam to this forum. She is working on the research area of shape memory alloys and smart materials, improved structural materials, additive and laser-based manufacturing, marine structural engineering, advanced alloys and super alloys. Madam has received AV Humboldt Fellowship, AV Humboldt Fellowship Germany, Institute Silver Medal at IIT Kharagpur, National Doctoral Fellowship, and Venus International Women Award. She has published more than 25 research articles in additive manufacturing, and she is currently working as co-principal investigator in the project of development of high performance materials for various defense related application, which is the project under DRDO. Madam has extensively working on additive manufacturing in the aspect of material science, and she is having he is guiding so many PhD scholars. It is our great pleasure to have some words from madam. It is I request you to share the session, madam.
Thank you, Professor Dinakaran. Thank you so much for this nice introduction and for giving me this opportunity to share my experience on the additive manufacturing kind of work that we do, which I understand may be a little different from whatever the mechanical engineer standpoint is. So with that, let me just share the screen to the participants. I cannot see the participants here, but I guess there are several participants already there who have a wonderful session so far. You must have listened to a lot of presentations on different aspects, different topics of additive manufacturing and 4.0. Okay. So just a minute. Yeah. So with that, let me just share the screen. Okay, my screen is visible to everyone.
Yes, ma'am. Please, you can go ahead, ma'am.
Okay, so to the starting, I would like to say that the topic of my talk was microstructure-property correlations of materials, and I thought that let me give you actually the perspective. So I want to give the talk today on the metallurgist perspective. How do we think of additive manufacturing when it comes to our knowledge? What are the things that we are mostly concerned with? So I will turn my video off, and I hope I am audible to everyone. And if there is any issue, please let me know.
Yes, ma'am. Yes, ma'am.
Sure. Okay. So at the first point, let me just show where do I belong. So I come from this IIT here, located at the eastern part of this country, and this is the first IIT for the entire IIT system that has been established in 1951 by our then Prime Minister, the first Prime Minister, Pandit Jawaharlal Nehru, and we do have a strong history in the sense that our campus is actually located in a Hijli detention camp. So this is for, there was a jail, there is actually still a jail for the freedom fighters of the then the dependent India, and when it was a motto to create a university which can cater to the strength of the country, it has been developed here. We still have the main motto of our institute is it's inscripted here as dedicated to the service of the nation. We strongly believe in that aspects, and Let me just show you the group of students, my entire strength, who have added up to my knowledge base layer by layer. Of course, this photo has been taken before the lockdown, so some of the faces have already, they have passed out, and there were some new faces to this. So whatever I'm going to show today are because of their hard work. And the broader research activity, what we do is basically we try to correlate the microstructure and the mechanical properties of materials. And materials means different kinds of materials. We work extensively on nickel titanium based shape memory alloy that has wonderful properties, on the titanium based intermetallic alloys, which are very much capable for high temperature application used in aerospace industries. And there are several other kind of titanium alloys, and of course anything to metallurgy will always stand on steel. So steel forms our main pillars. So there are several categories of steel that we work on, super alloys as well, and these are both conventionally processed as well as additively manufactured. We do extensively study their mechanical properties at the macro scale, doing several kinds of fracture, fatigue, kind of all different kinds of fatigues on this, and also at the micro and nano scale. Okay, I'm getting a message that the connection is interrupted. Am I still audible? Am I audible?
You're audible, ma'am. Ma'am, you're audible.
I'm audible. My screen is visible. Okay, I am not able to see my screen anymore.
Ma'am, you please, if anything, any disturbance, I will come back to you, ma'am. Please, you can talk comfortably, ma'am.
Fine.
Yeah.
Fine. So these are my contact information. If anybody would like to come back to me for any kind of assistance, I'll be happy to be in your support. Okay, so with this, let me just start today's presentation. So when we, the metallurgist, when we talk about any kind of process systems, we think of several kind of processing operations. Okay, when we are talking about the component, we think of several kind of processing operations which are inevitable, like casting and different kinds of machining, etc. Okay, so these are the some of the ways by which we actually try to give the material, a block of material, to a particular shape. We apply several kinds of machining operations like turning. Okay, let me just show a video, and since there is no sound in the video, so I will just explain it myself. So you see, this is a kind of straight turning where we apply the tool to turn it continuously so that we can give it a particular shape. Okay, and in the process you can see that there is a lot of chips that are coming out. Okay, so this is another way of turning that is being shown. So several kind of operations is the taper turnings, where we can get a taper, something like this. Of course, there are a lot of mechanics behind each of these operations, and I'm sure you might be familiar with these operations very much. So what we can see here is that to get a nice shape or the purpose that it is meant for, we actually need a lot of, after processing, after casting the materials, we have to go through a lot of a severe amount of processing to give it to the final shape and the required properties that it is meant to. So this is a kind of forming operation. And chamfering. So this is necessary to give it a 45-degree inclination. and this is grooving. Often we need to do internal grooving as well. Threading, you can see the threads very distinctly here. Okay, so these are the different operations that we need to do. Fine, but when we think of that, the thing that comes to our notice is that this is associated with a large number of problems, in the sense that we always thrive for better and better material, and by better we mean that it should have a higher strength, hardness, etc. Right? So higher the strength of the material, we would need the tool should have even more hardness compared to that. And when we are continuously machining, there is a huge amount of tool wear. So there is a lot of studies going on to have the tool material strong enough so that we can have the component of certain material like the super alloys, which are very much stronger, and we need to have such kind of tools. And wearing of the tool is a huge issue. There is, of course, undesirable chip formation. So you see the chips everywhere. We need to do some after processing as well to get rid of this chip, and basically this is just a wastage of material. So we have to waste more than 50% of the material just to give it the final shape, which is often very much challenging considering the entire cost of the component that we are talking about. So this is how conventional subtractive manufacturing turns to. We have a block of material to which we give the particular shape that we want to, and in turn, as I said, that there is a huge amount of material that is being just wasted. In comparison, when we turn on to additive manufacturing, we actually turn reverse. So we start with the powder and we end up creating this shape, whatever we require. And there is actually very minimal amount of waste. And even this kind of the additional powders can be reused. So we finally end up having a high efficiency of the process itself. So that saves us in many ways. So basically, a subtractive manufacturing is nothing but a top-down approach. We start with the bigger piece and we gradually move on to the kind of shape that we require based on several kind of operations. On the other hand, additive manufacturing, we start with the powder. So it's a bottom-up approach. We start from the lower level and then we keep on adding the layer by layer to finally reach our the shape that we require. Okay, my screen has once again gone and I'm getting a message that there is an interruption.
Ma'am, it is okay, ma'am.
Okay, fine.
Fine, ma'am.
Thank you. Okay, so if we just give the brief differences between the additive manufacturing and the subtractive manufacturing. As we say, the name itself, additive, goes on by adding layer by layer, whereas the subtractive one deals with removing from it. Right, we can get the complex and customized shape, whatever is necessary, we can do it. It is said that in single step we can do this in additive manufacturing, whereas in case of subtractive manufacturing, we have the limited ability. We often are not able to fabricate very complex shape just by machining it to different level. Okay, then there is another way which is very important, which is the porosity. So the density of the component can be controlled in case of additive manufacturing, whereas in here for the case of subtractive manufacturing, we do not have that much of control in fabricating a component with certain amount of porosity. There is a significantly reduced material wastage in case of additive manufacturing, whereas subtractive manufacturing, there is a major disadvantage here is that we have a huge amount of material wastage, and that is cannot be suitable for several reasons, such as the cost, the efficiency, the energy at every respect. Okay, so there is another thing which is a little bit crucial for additive manufacturing, is that these processes are applicable for only a narrow range of materials. So very few of the materials has been tested and explored in case of additive manufacturing, whereas for the case of subtractive manufacturing, we have different varieties of materials, a wide variety of materials that can be used. Okay, so if we think about the advantage of additive manufacturing versus subtractive manufacturing, okay, my slides are not moving. Okay, so we see that the main advantage of additive versus subtractive, other than material wastage, is that we have a significant control on the porosity, whereas it is impossible to control the porosity in case of subtractive manufacturing. On the other hand, in case of additive manufacturing, what is the disadvantage is that only a narrow range of material has been tested, explored here, whereas subtractive manufacturing is capable to do this for all kinds of materials. Okay, fine. Now, moving to the additive manufacturing itself, we have already established that additive manufacturing is the future. There is a lot of opportunities that can be done, and several things that need to be explored in case of additive manufacturing. We also need to understand that what are the challenges. Of course, there are several advantages, but what are typically the challenges that needs to be overcome in case of additive manufacturing. So first of all, we can get a complicated shape, but it is very challenging to have a fine accuracy of every nooks and corners of that. Often the surface finish is an issue, and we need to ensure that there is a suitable surface finish. Now, when we are talking again from this is both from the metallurgist or the mechanic point of view, when we think of a particular application, let's say an aerospace application, okay, we are very much concerned about different kind of properties, for example, fatigue, how the component will behave in case of cyclic loading. So if we are not able to ensure proper surface finish, that will be very much detrimental for the fatigue performance of the material. So we can have a complicated shape and we can have all different kind of benefits from additive manufacturing, but we can still end up having an early failure if we are not ensuring this one particular little guy here. Okay, so this is something that we need to be concerned of. The validation is required to ensure that there is a proper testing and data has been obtained. Okay. Another thing, the major disadvantage of additive manufacturing, or not disadvantage, we actually is something of concern, is that additive manufacturing leads to microstructural inhomogeneity. Okay, and that can have a variation in the properties altogether. So my talk will particularly focus on this particular aspect, that we need to understand and deal with that to have a better kind of microstructural homogeneity, so that the properties, the required properties, can be obtained. Of course, there are several advantages. One being that this is considered as a green technology. It uses much less amount of energy, and that leads to lesser emissions, so which is very good for our Mother Earth. So that is how we should always thrive on. And of course, another thing, since we are talking about the disadvantage due to microstructural inhomogeneity, there is an advantage too in the microstructure generation, is that it produces very finer microstructure, and we often end up having the additively manufactured materials having finer microstructure compared to its as cast counterparts, and we end up having a significant impact of that in the obtained properties. Okay, so these are the steps of additive manufacturing that are typically being followed. So we have to have a computer-aided design that is used, that is made using a modeling software to have the particular shape that we want to create, and convert that CAD data to the STL form and install that in the additive manufacturing machine. Set all the machine parameters. Now these parameters like the material, the powder, specification of the powders, the energy source, how much will be the wattage and all, the power, scan rate, energy density, addition strategy, often the direction on which these are being added, timing, etc. All these are very, very crucial, and any change on any of these parameters can lead to variation in the obtained microstructure, obtained component performance in general. Okay, and this is one of the reasons that all these parameters need to be validated first, tested and validated, that we could not use this the additive manufacturing on a large variety of materials. We are still limited to only a few materials. Well, few means a lot actually, but maybe not all the materials, because we have to understand the influence of all these parameters, the machining parameters on the component properties and the component shape. Okay, now once these are all set, it can build the part. It is completely automated, so we can just give the instruction to the machine and it can print it layer by layer, and then once it's done, we need to remove the build part, do the post-processing cleaning. Often if we need to do some kind of other post-processing like heat treatment, we may have to do that, and finally used in the application. Okay, so these are just the flowchart for that. And there are different kind of additive manufacturing processes. Okay, so according to the ASTM, there are 42 different ways. Out of that, the one which are mostly suitable for metallic systems are the powder bed fusion or powder feed technology. Okay, so amongst the powder bed, there are again different kind. There are electron beam melting, selective laser sintering, selective laser melting, and direct metal laser sintering. Whereas in case of powder feed, we have the lens, laser engineered net shaping, the direct metal deposition or laser metal deposition. These are the principal operations that we use. So basically, we have different kind of heat sources. We have laser beam, electron beam, plasma arc, gas metal arc. All different things are used as the energy sources, and again out of that, the laser beam is the one which is mostly used. Okay, electron beam is also very much used, but laser beam is the most widely used thing. And as I said, that the major two types of additive manufacturing technique which are mostly used for metal additive manufacturing are powder bed, where we have a nice bed of powder, and then there is a the source of energy is being traveled as per the design, and we get the product out of that. And in case of direct energy deposition, or often called powder feed, we have the energy source as well as the powder stream acted simultaneously as per the design, and then we are going to get the final product. Okay, so these are the different techniques for powder bed as well as the powder feed thing. And we just to highlight, I would like to show these two different things, which are one from each categories, to show how these are being done. Okay, once again, I'm having a video here. This is for the direct metal laser sintering. So once again, I confirmed with Professor Dinakaran that the sound is not audible, right? It is still not.
Yes, ma'am. Sound is not audible, ma'am.
Sound is not audible. Okay,
Yes,
so yeah, I will just go ahead with this. There are this is how it is being made, and just the video explains it elaborately. So So such a giant structure is being made. If we are, so this is a kind of stainless steel that they have used for aerospace application. These are all the layers that is being made as per the design. So this is the powder bed that is being forming. So again a powder bed, and then there is the laser as per the direction, as per the shape. And this is how it's going, the thickness. Now removing it from the base plate is also sometimes very much challenging. So all the support structure and everything needs to be removed and needs to be polished to have a smooth surface finish. So often DMLS is used for aerospace, for surgical implants, for different kind of tools. That is where we are going to use this. And this is the laser engineered net shaping system, which is a powder feed technique. So it's not a powder bed anymore. We apply the energy source as well as the powder simultaneously. This is just a system from Optomec that has been shown here. So there are the dual powder feeders. So this is repairing a key. This is another very good application of additive manufacturing, and lens is often used there. So if some part is broken, we do not need to replace that. We can simply remove that. So you can see that the powder and the laser coming from the same place, and it is doing this according to the scanning. And in the next step, we will see that it has turned it has been reoriented to 90 degree to the previous layer, so that finally we are going to get an uniform structure as much as possible. Often this angle between the different layers are varied. It's not always restricted to 90 degree. Okay. So coming to the metallic systems, which are mostly additive manufactured, we have seen that there are several metallic systems which are very much highly explored in case of additive manufacturing. The primary being stainless steel, of course, and then we have the aluminum, titanium, cobalt, chrome, superalloys, nickel superalloys, and some precious metals also. So at various fields of applications, these are being used. Aerospace, this forms aerospace and medical. This forms actually the major part where additively manufactured materials are used already in usage in such places. Partly also because they are always, aerospace and medical fields are always exploring new things. They need to ensure that whatever application criteria are required, whatever properties are required, that has to be met, and how best we can do that. In case of aerospace, one significant advantage of using additively manufactured component is that we often get rid of the additional attachments. For example, if we need to fix one component to the other with the help of welding and rivets and all. In case of additive manufactured things, we can get rid of such additional parts like the rivets or the weldings, and this often has been seen to cause the problem and lead to various catastrophic failure in case of aerospace application, also for medical. So in case of additive manufactured components, we can get rid of those and can minimize the chances for errors or the failures, the early failures. So they often explore several kind of things, titanium being the very widely used for both these fields, aerospace and medical. A lot of explorations has been already been done. And then in energy industries, automotive, marine, etc., there are many other fields where additively manufactured materials, metallic systems are being highly used and already in service, being commercialized. So if we talk about the metallurgist perspective of all this additively manufactured technology and what we get, we finally narrow down our things into two particular states. First of all, when we do additive manufacturing, how does that modify the microstructure of the component? Okay, so we deal with finally the microstructure. We go into the internal part and see how does the microstructure is getting altered. And when we do that, our next question is that how does that affect the properties of the component? Okay, so these two are inherently related. Okay, so if we have any control on this microstructure, we will be able to control the properties also. So based on the industry that is being using this additively manufactured components and based on the particular application area, we would like to control the microstructure and in turn have the properties of our requirement. So again, coming back to how does this microstructure, as I have already mentioned, that additive manufacturing, one of the biggest thing to notice from for a metallurgist is that it creates a non-uniformity in the microstructure, and this particularly is related to the heat distribution during the additive manufacturing process itself. So whatever excuse me, whatever heat source we are having, it actually leads to a variation, a gradient, and a different kind of radiation, conduction, all these kind of things are happening that leads to a formation of a gradient in the structure. So there is a temperature distribution, as you can see. So temperature varying from 2200 at the very inner part where the laser beam or whatever energy source is focusing in there, and at the end we are going to have a temperature of around 400. So there is a huge temperature difference between this. Of course, the entire process is very much localized. It happens layer by layer, and also within a layer also it is getting a very much localized. There is only a smaller part which is being melted, and then it gets solidified as the energy source moves to the adjacent part, the neighboring part, and this leads to a very strong distribution of temperature, and temperature gradient will also lead to variation in the melt pool. As you can see that there is again the shape and temperature level, everything for the melt pool has changed layer by layer. So this is the subsequent layers that has been shown. And we can see that at every layer this melt pool geometry is completely different. So again, if we look for the cooling rate, now the cooling rate is related to its distance of the additively manufactured component from the substrate near to the bottom and also near to the top. So there is a huge difference in between these two levels, and we can see that there is a drastic change in the conduction level and the cooling rate level with increasing layer numbers. Okay, now all this is finally affecting the formation of the microstructure there. So when we talk about microstructure for metallic system, we think about the grain structure. This is the very basic, the backbone of the microstructure. So we have a grain. Any kind of materials will have a structure like this. They have a grain and then the grain boundary. Okay, metallic systems at least. Okay, and within now these grains are actually formed of crystal lattices. There are different ways by which the atoms can be arranged, and we can have different kind of lattices, and these lattices finally will organize up to a certain extent. That is a grain, and it forms a boundary. So that's the interface between two different grains where this lattices are oriented along different directions, and all this are very much affecting the properties of the material. So let's see, a conventional materials will have microstructure something like this. This is a real scale microstructure seen in the microscope. This is how it looks like. This austenitic stainless steel, which has the grains very much prominent here. You can see varying phases also, the bluish phase versus the grayish phase here. This phases, ferrite and austenite, has completely different properties. Okay, then we can have slips and twins that will lead to the deformation, that assist to the deformation, and depending on the presence of this, we can also have different variation in the properties. This is an aluminium welded structure where we see different variation of grains here. So the columnar grains and equus grains of different orientation. So this color signifies the different orientations that the grains are aligned. This is a pure copper one, and this is the copper alloy having different phases with completely different hardness. So this is typical from what we get from the conventional systems. Okay, now when it comes to additive manufacturing things, now whatever this kind of structure is, we expect this structure to be uniform all throughout. So the entire component will, if we have a cross section and look it into the microscope, it will show us grains like this at any point, be it at the top or bottom or something. But in case of additively manufactured thing, we are going to have a completely different scenario. So what we have there is that there is a difference in the melt, cool, and the heat distribution, as I said, and that leads to variation in the microstructure within the same structure itself. So you can see this is a 3D one, and we can see such things, and we actually can figure out the layers, each of these layers, from the structure itself. We have equexed structure, dendritic structure. First of all, you can see big dendritic phases there, and then we have the equexed, columnar, all different kind of morphologies. And what eventually we get in the in additively manufactured component is that there is a modification in the microstructural size as well as the morphology. Okay, we may have, even if we have equexed grain, we can have fine equexed and coarse equexed, and then there can be columnar grains versus equexed grains. We may have different kind of phases altogether, and maybe not the different kind of phases are not only different with respect to the conventionally manufactured materials, but at one zone, at the top layer versus the bottom layer, we may have differences in the microstructural size, morphology, phases, as well as the composition also. Okay, so although we start with the same powder, we end up having different kind of composition at the different zones. It's possible. And the extent by which this variation will be there is dictated by the various processing parameters that are being imposed during the additive manufacturing technology itself. Okay, so while these are leading to the modification, we, the engineers and particularly the researchers, are very much excited to note that if there is some kind of modification, we are always not satisfied with the term modification. We want to control that. Right? That's how the term engineering is being used. So we want to engineer that out of our own requirement, out of our own wish, so that we can have a control on the properties, the final performance of the material. So this is what is being shown, that if we have a 3D component, something like this, and if we cut it at several sections, we will have a completely different microstructural lookout. So this is the XY plane versus YZ plane. You can see that there is a complete differences in the microstructure. Okay, and this at every layer, this is being different. So this is the build direction, and we can figure out the layers and how these are being made. So if we do this analysis at different sections, at different angles, we will see that there is a complete variation in the microstructure, and that means that there will be a complete anisotropy in the properties. The properties at these different layers will also be different. Okay, although subtle, but there can be huge differences between the top and the bottom versus the cross section and the perpendicular, and so on. So finally, we do not want our component to fail at be stronger at one direction and weaker at the other, right? So we try to homogenize it as much as possible. And also, these are the typical features that we would see in additively manufactured things. The first thing that we notice is this kind of fish scaling, the hat spacing and all, that I will just discuss a little bit from now. But other than that, there are some defects that are formed. There's some balling effect, there's some unmelted part that can retain there, and there could be some hot tear between the layers, and this could lead to weaken the structure, and this could lead to some failure. Since one of my focus is also to study the mechanical properties and particularly fatigue, such kind of cracks in between all these balls here are very bad news for the fatigue behavior of the material. Okay, so also everything is under control. We want to get a final shape. We give them the design. The machine is actually doing it layer by layer wonderfully, but still there could be some mismatch at some point, leading to some unmelted zones or some tears or cracks that are forming, can lead to discard the entire component as a whole. So we have to be very much critical about setting the parameters to get the thing that we want. And before that, we need to evaluate it thoroughly. So even if we are able to manufacture a component, that is not the end of the job. Our task, being a metallurgist, our task starts from there to ensure that if every part has been made with whatever is required to attain the properties that is meant to be. So then I'm going to show you how this microstructure properties are usually correlated in case of additively manufactured metallic systems, and I will do that with 4 typical systems. One which is non-ferrous but very widely used titanium alloy, and then a functional material, as I said, shape memory alloy, nickel titanium, which has very much niche applications, both in case of aerospace, space, as well as in biomedical industries. And of course, when it comes to metals, we are always biased to be on stainless steel, and there are so many applications of stainless steel. So I have selected 2 different categories of stainless steel for today's presentation. So let's just move on with the microstructure property correlations. And before going on to this 4 different materials, I'd like to give you a brief understanding of how this microstructure and properties are correlated. So this guy here is actually the structure. Structure refers here as the microstructure, and microstructure means the grain structure that I just explained. There are various other features of microstructure which are of importance, such as the lathe structure, colony structure, etc. So how these crystal lattices are being oriented and distributed, that is how it dictates the structure, and it finally controls the properties. We do several kind of characterizations to get the properties. Well, this structure is finally being controlled by the processing. So actually this thing starts from here. We process something, be it conventionally processed and as cast and then machined, or be it additive manufacturing. So based on the processing, we end up having different kind of microstructure, characterize it, and based on the different kind of microstructure, we get different kind of properties which finally dictates the performance of the component. Okay, so this is how it leads to processing, structure, properties, and performance. And this is just an example of the different techniques and how and what this can alter. So we have seen that in case of additive manufacturing, it has an influence on almost everything, all the aspects of the structure, the microstructure, including the phases, the grain sizes, morphologies, the densification, porosity, segregation, etc. And these are again leading to variation in the important properties which are of relevance, such as the strength, ductility, toughness, fatigue. Hot cracking resistance often is related to the segregation of different phases, etc., and which is finally dictating the performance. So moving on to the most commonly used titanium alloy, it's a titanium 6 aluminum 4 vanadium alloy. That's a two-phase titanium alloy. It has two important phases, alpha and the beta. One is the alpha phase is a comparatively low temperature phases, which at high temperature converts to a beta phase, having a completely different crystal structure. Alpha has an HCP1 and beta has a BCC1. Okay, so when we look into the additively manufactured structure, this is how it looks like, a macro structure. You can see this bands here very clear, and this actually signifies the grains, the prior beta grains also can be seen here quite big. And if we investigate the microstructure at the different levels, at the different layers, starting from B to G, you will see that there is a distinct changes in the microstructure. This is very much fascinating. Okay, this is the electron backscattered diffraction images where we see this microstructural changes very, very clearly. So we have this columnar lathe. So this is called lathe structure in case of the alpha and the beta. We have this comparatively gray phases is the alpha, and then the white phase here is the beta, which is seen here as red and black. Okay, or the greenish actually, black. So we can see that this can be columnar, this can be more or less equiax, and the size also is decreasing, and we have a completely refined structure. That is what we are seeing. And of course, this has a huge role to play when we are talking about the strength and hardness, because the microstructural size somehow is inversely related to the strength of the material. I'm sure you might be familiar with the Hall-Petch relation, which says that the strength, the yield strength of the material is inversely related to the square root of the grain size or lathe size or any kind of microstructural size. So as we have finer and finer microstructure, we have higher and higher hardness or strength. So this is what it is showing here. The interesting thing here is that this is a base material. This is a reference which is for the forged conventionally processed titanium alloy, same alloy, and it has a hardness of only around 350, whereas if we keep if we have the additively manufactured component, the hardness is always at a higher level compared to the base structure. And this is again because of the additive manufacturing being able to produce finer microstructure. Of course, there is a variation in the microstructure, size and morphology, and that leads to a variation in the hardness level also. Okay, and highest hardness is noted for the equiax structure. So we always should strive for that. Okay, now and there is another work here which shows that even if we use additive manufacturing, if we use two different kind of additive manufacturing technique, one is the lens, laser engineered net shaping, versus selective laser melting, starting with the same powder. So it's the same, it's a pure titanium, commercially pure titanium. If we start with the same powder and just apply two different kind of additive manufacturing technique, we are going to see completely different microstructure at the same level. So if we are looking this at the low magnification, we see that the lens one is producing much finer microstructure. That is what is apparent. It's not very clear here. Whereas if we look into the higher magnification microstructure, we'll see that in fact the SLM1 leads to formation of the martensitic structure. Okay, this fine acicular alpha prime, these are nothing but the martensitic structure, and martensite structures have a lot of other benefits. It usually is very much harder compared to the normal alpha phase. Okay, so obviously that will lead to a variation in their properties. So this is the stress strain diagram, and we see that while the cast one, the conventionally processed one, and the lens one are more or less comparable, the SLM one, because they are producing this martensitic structure, is going to give us higher strength, higher UTS for failure. Okay, so the SLM1 could be preferred in that sense. Okay, now when we do that, we are not always happy with this term that SLM gives us better structure. Again, the question is why and how. Okay, to answer that, we need to understand that we can also vary for each of this process, be it SLM or be it lens. We can also vary the parameters, the processing parameters, the power, the scan speed, as well as the powder flow rate, to end up having completely different kind of microstructure. So you see here, we are using the same power. This two microstructure, if we are considering at the top, we are using the same power of 200 watt and the same scan speed of 10 millimeter per second, but just there is a difference in the powder flow rate. The powder flow rate is higher, double in this case, and we are ending up having a coarser microstructure. Okay, and in comparison to here, we are actually reducing the power and increasing the scan speed, but with the same flow rate as this one, and we end up still having coarser microstructure. Okay, so we now have the way to figure out that, okay, which kind of microstructure we need to attain the properties of a requirement. It's not always mandatory that we will thrive for higher and higher hardness, because higher hardness also comes with lower ductility. So we have to optimize it, optimize the processing parameters to end up having an improved property. And while doing that, there has been a study to find out the relative density. This is another very much important part, because if we are not producing a dense component, and if we are ending up having porosities, voids, or some unmelted zones there, that could lead to failure for several ways. Okay, so what we can see here is that in case of lens processed specimen, we can achieve the maximum density, which is more than 99% at an energy of around 146 joule per millimeter cube. Okay, whereas in this case of SLM, because of the technique itself, the differences in the techniques will lead to achieve us the same amount of relative density, but with a much lesser energy density. Okay, this is the lens versus SLM, the defects that are being formed here, and you can see that there is a lack of fusion that leads to crack generation, such big cracks more than 100 micrometer size, and these are completely a bad news for any kind of application that requires cyclic loading, or even for normal tensile purpose also. So if we end up having something like this, that component is of no use. So we have to be ensuring that, and we have to use this particular energy density, change the processing parameters to have that. Whereas if we are using this energy density of, as I said, the 146 for the case of lens versus 120 for the case of SLM, we end up having a completely compact structure with no such defects. Okay, so we can see from here that SLM will require lower energy, so should be cost effective, and also we can change the phases. We may form martensite. That will be a good news if we are talking about the hardness of the material. So there has been some extensive reviews done on different kind of processing technologies that has been used, the conventional heat treatment versus different kind of additive manufacturing, such as lens or DMLS or EBM, DMD, direct metal deposition, all these things, and we have a very nice summary of how the properties are varying: the ultimate tensile strength, yield strength, and elongation. These are the three primary properties that we look for other than fatigue, and these are varying extensively if we are talking about the cast versus the additively manufactured, as well as amongst the different additive manufacturing things itself. So based on the requirement, we can figure out that which of the technique is suitable for a particular application, and we can go ahead with that. Okay, so what we can take away from this part is that there is a huge differences in the microstructure and as well as the property if we are doing this along the build direction. Okay, from bottom to top, there is a variation in the microstructural size, morphology, as well as phases, and that can lead to differences in the properties, as well as different aim processes, be it SLM versus lens or any other kind of processing techniques versus the conventional one, that influences the microstructure and properties in a big way. And we have to understand that we need to correlate that very methodically and systematically to use it for any particular application. Okay. Any question in between? You may interrupt me, or I will move on to the.
Ma'am, please, you can go ahead, ma'am. Last week, take me.
Okay, fine. So next, let's move on to the nitinol, very popular name. You must have heard about this name, nitinol, which is used as a smart material. It's a functional material used for various smart applications. So before going on to the details of the additively manufactured, so we have worked on something on the lens processed nitinol, and before going into the details for that, I would like to give just a brief introduction of this system as such, because this is a very much unique one, and just to ensure that all of you are familiar with what we are talking about. So this material also has two different phases. One is called austenite and another is martensite. It's different, completely different from the martensite that we have just seen in case of titanium or what we regularly see in case of steel. This has just two different crystal structure that can be achieved if we are applying stress or temperature. Okay, so this shows that if we have the initial structure as the austenite one, austenite has a cubic structure, okay, and if we apply stress to it, it is going to transform to martensite. Simply by applying stress can lead to change into martensite, okay, which is having a monoclinic structure, okay, and afterwards, if you keep on adding stress, there is a huge amount of strain that it generates, but there's a very minor amount of stress that is required, and it basically does a detwinning of the martensite. So initially it formed a twinned martensite and it gets stretched out. It forms detwinning martensite if we keep on adding the stress, and we get a large amount of strain. Now the beauty is that if we are unloading, so after there, if we are simply removing the load, we can go back to the initial austenite phase, and this entire amount of strain can be completely recovered. That is why it is called shape memory. So whatever shape change that is happening, it looks like the typical stress strain curve, but it actually, so this part actually can be completely recovered. Okay, so up to this, if we do not have this unloading section itself, this will look like a typical stress strain curve, but what it actually does is it can completely recover its shape back. Okay, now this has various applications. This is used even for the wheels for the lunar vehicles. The one that is used in moon, the lunar rover, it's called. The wheels are made of this nickel titanium, which can simply go ahead with any kind of rugged surface, because it does not have any plastic deformation. Okay, and all this whatever phase transformation that we are achieving with a stress can be also achieved by changing the temperature. Okay, at one particular temperature it changes to austenite to martensite, and if we reheat that, we can get back to the austenite. Okay, so this is a completely reversible hysteresis that can form. Okay, so as I said, it is used in very niche application like in lunar vehicles, but in most commonly this material is biocompatible. So that's why it is also used for various medical application and implants. One of the very important application of nickel titanium is it is used in cardiovascular stent, the one that we use to remove the clot in our arteries when we have any cardiac arrest because of the cholesterol problem. So you can see that this is an artery where the blood flows and there is a clot here, and if we use a stent made of nickel titanium, because of the temperature and the stress, it can expand, can have a different shape, and that can expand the blood vessels, remove the clot, and the blood can easily flow through that. So that's a very nice application of nickel titanium, and it is being largely used. Now, when we are talking about medical application, we often need very complicated shape and miniaturized. Okay, these are hardly a millimeter size, and we have even this is used also as sensors in MEMS. So we have micron sized devices and implants that need to be made, and often we have to take the advantage of additive manufacturing to make that. So this particular one, we have used a lens system to have the nickel titanium component, and in the process we have varied the processing parameters. We have used 3 different laser energy densities starting from 27 to 70 joule per millimeter cube, and we have actually varied the laser power, scanning speed, etc., diameter, and we end up having 3 different laser energy densities. Okay, although we started with the same powder, same nickel titanium pre-alloyed powder. Now, interestingly, okay, what we get is a completely, it looks the same, the 3 component that we are getting out of the 3 processing energy densities. We have done a thorough microstructural characterization at the first step from the various locations, from the top, middle, bottom, cross section, parallel to the build direction, perpendicular to the build direction, interior of the build direction at every location. And what we have seen that for a particular location, this we have named this as E1, E2, E3, where E1 is made with the lowest energy and E3 is with the highest energy, and we can see that there is a complete differences in the microstructure. This is the typical optical microstructure in the tint etched condition. So that's how we can generate this colorful microstructure optically. And this is the EBSD one, which shows this layer structure very clearly. But if we go into the more detailed structure, we have seen that this kind of layered structure with hatches present are very distinctly visible. Okay, now based on the laser tip here, we generate such kind of hatch structures. Okay, and looking onto this very carefully, we have seen that there are different morphologies that are forming. So we have the coarse equiax kind of structure, we have the columnar structure, and then we have the very fine equiax structures also. So the fine equiax structures have something like grain size of 4 to 5 micrometer, whereas the coarse equiax one is having 5 times higher than that. Okay, so obviously this will have a huge influence in the properties too. So this is how the hatch structures is being formed, and we have characterized this hatch structures, hatch spacing and layer thickness, and we have seen that this also varies distinctly for the 3 different energy densities that we have used. Most interestingly, the one prepared with the highest energy densities has shown us some precipitates forming there. Okay, now these precipitates are some the TI rich precipitates that are forming, and this certainly will have a huge role to play in the properties of the material. We just look into that shortly. Okay, now another interesting thing is the porosity. As I said, that porosity is something that we can control, and this video shows here that we have analyzed it through microcomputational tomography and see how the porosities has been developed all throughout the component. And this is for one particular alloy system, made with the highest energy density, but if we compare just the three of them, we will see that the one prepared with the lowest energy density has a lot of porosities in them. Okay, so considering our applications, whether these porosities will be beneficial or not, we can figure out that what kind of processing parameters are necessary. Well, porosities are, as I said, very much bad news for the case of fatigue applications, where we know that there is a cyclic loading. For example, in case of stents, also there is a cyclic loading. Our blood gets periodically pumped, like right, our heart periodically pumps. So there is a continuous cyclic loading that we are having. So any kind of porosities or any defects for such applications are bad news. On the same hand, if we are talking about some other implants, for bone implants, for example, porosity is often desired. Okay, so biomedical applications often require porosities of certain percentages, and for that, additive manufacturing is of great help, because we can control the porosities and even the structures and the positions also according to our need. Okay, so for this particular study, we have seen that as we are increasing the laser density, of course, the compaction is much better, and we end up having lesser and lesser amount of porosities. Okay, coming to the phase structures, we have seen this E31, as I said, this develops some amount of precipitates, as well as it generates some martensite phase also. Okay, as I explained, all the pseudoelasticity or the shape memory effect is coming because of the transformation of the austenite to martensite. So presence of any martensite actually hampers this process, and we will end up having less amount of recoverable strain in that case. So this is also being reflected in their DSC response, which is the conversion from the austenite to martensite due to temperature change. And we have seen that the one prepared with the highest energy density, that has the austenite finish temperature being quite high, higher than even the room temperature. So this leads to some variation in the properties. Okay, so the first thing we did is we did the macro indentation with applying very high amount of load, 500 Newton, and we actually could not see any difference in the hardness. Very happy about that although we are changing the processing parameters significantly, there is no such effect in the hardness behavior. Fine. But as we have done the micro and the nano indentation, things are different. Particularly in the nano indentation, we have seen that there is a huge change in the hardness, and that is being reflected because of the change in the phases present and the local structures of the grains. Okay, so this is what we have seen, that the presence of martensite and the precipitates that enhance the hardness and elastic modulus of the alloy, which is produced with the highest energy density. Okay, so far people would have been happy that, okay, if we are increasing the energy density, we end up having lesser porosity and we will have higher hardness. But that may not be the case, since we are talking about the pseudoelastic material, okay, which is capable of recovering its shape. So if what we mean by that is that we did nano indentation using, again, different kind of parameters very specifically suitable for pseudoelasticity, which is beyond the scope of today's presentation, but you just need to understand that we characterized it with nano indentation to find out the local recoverability, the ability of the material to recover the strain that is being applied. So in case of aluminum, you can see that it is completely not recoverable. Okay, huge amount of plasticity. We know that aluminum is very, very ductile. Steel has a little bit lesser one. And nickel titanium, we can see that major part of the load that we are applying is being recovered. Okay, so this significant part is being recovered completely. So this is because of some internal activities of the phase transformation that is happening to it. Anyway, this entire green and yellow part is being recovered. That leads to the recoverability or the pseudoelasticity of the system. Okay, now what we have seen to our surprise is that the one prepared with a moderate amount of energy, actually the green one shows the most amount of recoverability, whereas the red one, which is the one prepared with the highest amount of energy density, although it shows higher strength, it shows very high amount of plasticity also, which means that its recoverability or its shape memory capability is much lesser. Okay, now we require nickel titanium for application which is dependent on its strain recoverability or shape recoverability, right? More than the strength, this is the critical parameter, this is the critical property that we are concerned of. So obviously this study shows here that if we use a particular amount of energy, moderate amount of energy, lesser energy density while preparing, then only we'll be able to recover the maximum amount of strain or load or whatever it is. Okay, shape basically. So this is what is being figured out, and we have found out a way to draw the nanoindentation stress strain curve also. We have also done the bulk scale testing to figure out this, and you can see that the one which is prepared with a moderate amount of energy, that gives us the nicest plateau and maximum ductility and so on. Okay, this has been also correlated with the digital image correlation. While tensile testing, we have figured out how the deformation is happening at every respect to find out. So you can see it from here that as we are applying the strain, the color coding here is changing, signifying the amount of stress is being applied, and this is loading and unloading, and then again loading. And we could figure out that for the three distinctly different components produced by different energy densities can have different properties based on that. And if we simply do the normal tensile testing, we will not be able to figure that out. I mean, if we simply do the hardness testing, we will not be able to figure that out, whereas we can find out from their tensile behavior the pseudoelastic nature of this material. Okay, so the bottom line is we require the optimized lesser energy density. So instead of low or high, we require a particular value or an optimized value to have a completely pseudoelastic behavior along with more or less ideal microstructure and phase. Okay. Now, moving back to the category, the next category of material, steel. Since we talked about nickel titanium so far, so let's start with the steel, which is also a biomedical grade. Or most of the things presently are being made of 316L steel. Biomedical implants like the orthodontic arches, etc., braces that we use are mostly made of this 316L steel. So this has several importance in the sense that it has high corrosion resistance, and it has a required amount of strength that is required for such kind of application. It has biocompatibility as well, durability, etc., and being used for several things like the surgical tools also. So not only as implants but also used for various surgical tools as well as implants as hip joints, screws, many such things, as well as in regular application in aerospace application as well. So considering the wide applicability of this material, additive manufacturing is also being tried on this material, and we have an LMD manufactured block, laser manufactured block, which we have characterized again at the different sections and cross sections, and which are parallel and perpendicular to the build direction, and then we have evaluated the microstructures at the top, middle and bottom at different sections and have seen the differences in the microstructure. So created a montage by stitching hundreds of images, and you can see that the layered structure is very much evident from here. If we look closely onto each of this, we can see the hatch spacing and the layer thickness very clearly. We have characterized that, quantified that, and we have seen that in each layer the microstructure is changing distinctly. Okay, you can figure that out at very even not so high magnification microstructure, optical microstructure itself. Okay, so this leads to different kind of structures, microstructures, in the sense that it has equiaxed, it has columnar structure, and the interface is often very much plays an influential role in dictating the properties of the materials as well. The layered structure is also evident. The interface is very much evident from the EBSD structure itself. Okay, so what we did in this case is we have the such variation in the microstructure, and to get rid of that we have solutionized them. So we have manufactured the component by additive manufacturing, and then we have used the conventional heat treatment procedure just to modify the microstructure, to homogenize the microstructure. So we have done the XRD to make sure that there is no further formation of any phases or anything that is happening, but the microstructure is getting equiaxed now. Instead of a variation in the microstructure as columnar and equiaxed and coarse and fine equiaxed, we have a homogenized microstructure of equiaxed grains all throughout, and there is no variation in the phase formation. Okay, so we have simply solutionized it, and then we have did a detailed study on the hardness, variation in the hardness at various level, at the micro, macro and nano hardness level, as well as we have done the tensile testing of this also. Okay, and interestingly, it has been seen that, so this is the as-built structure. Okay, this circular points here is the as-built tensile strength, and what we can see here, although the strength is the ultimate tensile strength, or the yield strength is higher in this case, but if we are using a solutionized additively manufactured material, we can see that there is a huge rise in the ductility. It has more than 50% of the strain to failure. Okay, so that leads to higher toughness of the material also, right? So if we are requiring for application which is mostly thriving on the higher improved toughness and improved ductility, we should definitely do some conventional heat treatment to the additively manufactured part so that we can achieve these properties very easily, although it will still have a higher value of yield strength compared to the conventionally manufactured materials. That is what we have figured out, and so based on our requirement we can simply do this. In a similar way, we have also studied the properties of 15.5 precipitation hardened steel. So this is a kind of steel which can be hardened further if we allow it to precipitate out. Okay, so this is being prepared by DMLS technique, direct metal laser sintering, and we have prepared a key kind of structure with this, and what we have figured out that the typical hatch structures and the typical additive manufacturing structures are already there, and once again the differences in the microstructure is quite apparent. We have the columnar, the cellular structures as well as the equiaxed structures as well, and these are varying with the build direction at every point. And what we did in this case is that apart from the as-built one, we have also heat treated the conventional aging treatment that is being used for this precipitation hardened alloy, because this precipitation hardened alloy, unless we do this kind of aging treatment, we are not able to get the full benefit of the precipitation hardening, right? So we have tried to implement the same kind of heat treatment that is being used for conventional testing, and we could see that the precipitates could come out at such temperature changes, and we have figured out that what is the optimum kind of heat treatment that needs to be done on this additively manufactured materials. If we want to use this precipitation hardened steel, we should use this optimized heat treatment as well, so that we can have the best of all the properties. And we did the XRD studies for all the structures. So we have the as-built structure, the solutionized one, as well as the aging treatment at 2 different temperature and time. Okay, and the as-built structure has also been studied, at the cross-sectional and parallel plane to find out the differences. We have also done the detailed porosity analysis, and most importantly, the corrosion behavior of this. And all this has shown a detailed systematic investigation has been done, and all these have shown that if we are aging it for 900, the condition is here. So the red one actually, so the red here signifies the one which is as built and then heat treated at 900 Fahrenheit for 4 hours. We end up having improved properties, almost all kinds of properties, and very high corrosion resistance also. So considering its application, that will be a huge implication of property enhancement. So this is the indentation studies that has been done, nano indentation studies, and for all the things for the top, bottom, cross-sectional plane, as well as a solutionized and aged at 2 different conditions, we will see that how the hardness are being varied, and we get the best one if we are heat treating it at a particular temperature and time combination of the additively manufactured one. We are not satisfied with doing only the micro scale studies, and we did the regular tensile testing as well, using the extensometer to figure out that which of the ways, and once again the red one, which signifies the aged one, shows the best of all the properties. Okay, so we could figure out that this condition is required. If we want to use additively manufactured component, we still have to go through this kind of heat treatment to get the best of all the properties. Okay, so again, the takeaway note for this is that overall, we see in the metallic systems, there is a huge difference in the microstructure and that to the properties. There's an anisotropy along the build direction, and the conventional heat treatment procedures in the stainless steel components can actually lead to further homogenize the microstructure as well as to achieve the isotropic and improved performance. So that was our goal, to make a component which will have even improved properties compared to the conventional manufactured one. And if we just do a little bit more along with additive manufacturing, we'll end up having that. Okay, so this is okay, just at the end, this is the Center of Excellence that is built at IIT Kharagpur, Center of Excellence in Advanced Manufacturing Technique, where we have several facilities, including the additive manufacturing thing, and then we have several other characterization facilities also. I'm partly involved in this center. And we have several kind of experimental facilities, characterizing tools for that. And of course, this would not have been possible without my students. There are many of them, as well as my collaborators all throughout the world, who has supplied us materials. In India, there are the Central Glass and Ceramic Research Institute, and then the Bhabha Atomic Research Center, the Defense Metallurgical Research Lab, as well as in the USA and Germany. There are several collaborators who are helping me to provide me the materials and to get this collaborative work ongoing. So thank you for patiently listening to me, and I'll be happy to answer. I hope I have finished in time.
Yes, ma'am. Thank you so much. The lecture was easily followable, and I hope all the participants might have got some enhancement in the knowledge, because metallurgical aspect, it is tough to understand and teach also. So you have nicely taught to the audience. So thank you once again, madam. So this lecture was entirely different than other lecture, because so no one has covered the metallurgical aspects in the additive manufacturing. So you have given in a different way. So thank you so much for sharing your wonderful experience, ma'am. Let me see the chat box for any questions, ma'am. How can we, Amit Kumar asked one question. How can we reduce the fatigue development in shape memory alloys?
Fatigue development.
Yes, ma'am.
Okay, see, fatigue in case of shape memory alloy is very, very crucial in the sense that because of the repeated phase transformation, it develops another kind of fatigue, which is called functional fatigue. Okay, it is continuously converting to austenite to martensite and then back to austenite and to martensite and back to austenite and so on. Okay, so along with the mechanical fatigue, there is this functional fatigue that is also happening. So we have a series of work done on that at different scales and high cycle and low cycle fatigue, etc. If we want to minimize fatigue development, means we have to use the right kind of composition so that we can at least minimize the functional fatigue. And this composition actually helps the conversion of austenite to martensite. Either it helps or it prevents, depending on the composition. And we have to rightly choose the stress amplitude or the mean stress to reduce the fatigue. So depending on the application, we have to select the right composition, the right stress amplitude to achieve the best properties in case of interdiagonal.
Thank you. Thank you. Madam, when should we choose low cycle fatigue and when should we choose high cycle fatigue?
Okay. The basic difference between low cycle and high cycle fatigue, as the name says, is that low cycle fatigue survives for lower number of cycles, right? So in case we have a higher applied stress so that the material is already in the plastic regime, okay, it goes to the plastic deformation. Plastic deformation is permanent. There is no recovery from that, right? So if we are applying higher amount of stress or strain during the application, but not high enough that it will fail at one go, but it is still at a higher level, exceeding the yield point of the material, then we will choose for the low cycle fatigue. It should have improved low cycle fatigue performances. If we are talking about repeated cycles for many number of cycles, usually 10 to the power 6, 10 to the power 7 number of cycles, but we are applying stress which is much below even the yield strength. So typically, ideally, a material, if we are applying stress below the yield strength, it is not supposed to fail because it is going only elastic deformation. It's not yet exceeding the yield point, right? So it's not supposed to fail. But because of some local deformation, it may. So if we know that the applicable stress is not high enough, let's say 50% of the yield strength of the material, we can go for high cycle fatigue.
Yes, ma'am. Thank you, ma'am. Nice, thank you for nice explanation. And Mr. Samuel Raj also asked one question. Should heat treatment always be carried out after AM of metals? Will the heat treatment procedure not engineered, not affect the engineered microstructure?
Heat treatment will affect the engineered microstructure. That is the purpose. Heat treatment is not always necessary. In most of the cases, when we advertise of additive manufacturing and the advantages of additive manufacturing, if you are making a turbine blade, okay, a big one with additive manufacturing, of course, doing a heat treatment for that will be very, very challenging. We need to have a furnace like that of that order, right? So heat treatment is not done usually. But if we are talking about very critical applications, then it is not desirable to have variation in the properties at the different parts. Right, so that will lead to failure. So if we are talking about such critical application, then heat treatment is suitable to give us the best. Of course, additive manufacturing has improved properties also. We have seen that compared to the base metal, a conventionally manufactured one, additive manufacturing itself gives a higher strength or hardness. But along with that, we also want it to be uniform and isotropic, right? We do not want it to fail from one side when we are, it is very much strong on the other side. So if we need to achieve that, depending on the application, heat treatment is always preferable.
Okay, ma'am. Thank you, ma'am. Thank you so much, ma'am. How to ensure the uniformity in powder bonding in powder bed fusion techniques?
That depends on the processing parameters. The different processing parameters, we can go ahead and change the powder bonding thing.
Yes, ma'am. Okay, ma'am. Thank you, ma'am. Thank you so much for your nice session, nice explanation. We would like to meet you in some other
Sure.
webinars or FTP. Thank you, ma'am. We will meet again, ma'am. Thank you.
Okay. Thank you very much. Thank you.
Participants, thank you so much for being in the FTP. So the next well-ready session and written test will be after 2 o'clock. So 2 to 2:20, there will be a well-ready section. After well-ready session, you will have written test. Test. The test will be through Google form. So don't worry about the questions. It will be very easy, and that what you have learned from the what we call this from this FTP. So if anybody is interested to share your feedback in online, so please you can text me in WhatsApp. So you can come and interact in this live session. So if any two male faculty members and 2 female faculty members are ready to share their feedback, it is well and good. So please text me through WhatsApp. Okay. So test will after 2 to 2:20. Please attend the validation session. So after that, immediately I will release the post the link for the test. So you can take the test within 2:30 to 3 o'clock. You can take the test. Okay. So thank you so much. Thank you so much for joining with us. Thank you.